Ancient Romans used a catapult to launch rock boulders at its enemy. One such catapult has prongs which are 24 meters apart. An elastic rope which has a natural length of 26 meters long. A rock boulder mass of 60 kilograms is placed at the midpoint of the elastic rope, which is being pulled back so that the rope is taut. The boulder is pulled back a further 11 meters, and the force required to keep it in this position is 400 newtons. Find A, the stretch of length of the rope, B, the tension in the rope and the modulus of elasticity, and the elastic potential energy stored in the rope and the speed of the boulder when the rope regains its natural length. So we are going to have to make some assumptions though. I'm going to assume that both of the prongs are rigid, i.e. there is no elasticity in the frame of the catapult, so all these things are rigid, which is probably not true in real life, and also that it's being fired horizontally, so it's not actually being fired at an angle, it's being fired horizontally. First thing, like in all problems like this, you need to draw a diagram of the system. So here we have the two prongs, we have the rope being taut to 26 meters from here to here, boulder being placed in, it's pulled back here and a further 11 meters, and then it's going to be released. These two are 24 meters apart, so we can calculate this distance here by using Pythagoras' theorem. This is the right angle triangle, so using this triangle here, MP1 is going to be 13 squared minus 12 squared. This is the longest side, the hypotenuse of this right angle triangle. We want half this distance, which is 12. So we do a subtraction on Pythagoras' theorem, which is 5 meters. So this length here is 5 meters. Therefore, MP2 from here to here will be 5 meters plus the 11, which makes 16 meters. And then using Pythagoras' theorem again on this big triangle here, so that's AMP2. We're now going to find this length here. AP2 is going to be the square root of 12 squared plus 16 squared, which is square root of 400, which is 20 meters. So this length for this one here is 20 meters. Right, so the stretch length of the string will be that plus that. So the stretch length of the rope, is 2 times 20, which is 40 meters. B, let the tension in the rope be T newtons. So the tension will be going in this way T newtons, and the tension up here in T newtons. If we resolve parallel to this line here, then 2T cos theta, because two lots of them, because it's going to be cos of this angle and next to the angle, must be equal to the 400 newtons going downwards. So at this stage the system is in equilibrium, but we can just say that cos is going to be 16 over 20, because this length here is 16 adjacent to the angle. This length here we just worked out to be 20. So that's for 4 over 5. Then substitute that in, we're going to get 2t, 4 over 5 is equal to 400, and rearranging that you get that t is 250 newtons. So we've got a tension here 250 in the rope. The extension x in the rope is equal to the stretch length minus the natural length. The stretch length was 40, the natural length is 26, this length here is 26, which gives me an extension of 40 meters. So if we're now finding the modulus of elasticity using Hooke's law says the tension is equal to lambda x over L. So it's going to be 250 is equal to lambda times 14 divided by 26. So lambda will be, if you rearrange that, 464.285 newtons, which rounded off to three significant figures will be 464 newtons to 300 three significant figures. Now the elastic potential energy stored in this rope is given by lambda x squared over 2L. So we're going to take the value of lambda, which is 464.285 times 14 squared divided by 2 times 26, which gives me 1,750 joules. Now, by using the principle of conservation of energy, this stored potential, elastic potential energy will be equal to the kinetic energy given to the boulder. So, kinetic energy is a half mv squared, so therefore this is equal to this. So we've got 1,750 is equal to a half times 60 times v squared. So that gives that v squared will be 58.3 recurring, and therefore the velocity will be 7.64 meters per second, correct to three significant figures.